The Ben Heck Show is brought to you by Element 14, the electronic design community and online store built for engineers and hobbyists alike. Join now and browse the store at element14.com.
Hello and welcome back to the Ben Heck Show. Recently we posted some bonus footage regarding 3D printers. However, many of you had additional questions regarding the content. So in today's episode, we're going to dive more in depth into 3D printers, the types of printers, what they can do, the parts in them, and how they work. Let's get started.
Amazing builds, exclusive mods, cutting-edge ideas, electronics, engineering, and more. Every week on Element 14's The Ben Heck Show.
Let's start by talking about the three most common kinds of 3D printers you might come across. FDM, which stands for Fused Deposition Modeling. This is by far the most common. That's when plastic or some sort of substrate is heated and extruded into a thin line and moved layer by layer to create a 3D object. STL, which in this case stands for stereolithography. That is when you have a vat of UV curable resin and a build platform. The laser is actually drawn with galvanometers to create the shape one layer at a time, curing the resin, creating an object. It's kind of like an FDM printer, but upside down. Although you could have an FDM printer upside down if you wanted, it would still work. The third type, which isn't as common, is powder deposition printing. This is when you have a powder or some other substrate that's, fine powder, looks like flour. It's in a bin, and a print head comes over, and it's very much like an inkjet printer, but instead of ink, it prints a binding agent, or it could be a binding agent with color to create a 3D print. It does that layer by layer until a solid object is created, basically glued together in the powder and pulled out. So we're going to be talking about FDM printing in this episode, so let's take a look at some of the parts of a typical FDM printer. I've laid out the basic mechanical parts of a 3D printer here. Let's go through them. First of all, you have your hot end. This is what actually extrudes the plastic. That's going to be around $75. This is a nice Prusa hot end, for instance. Then you're going to have your build platform. If you have a heated platform like this, that's probably going to cost you around $25. Then we have motors. We have the Z-axis. There's two of them usually, so it can move up and down. Sometimes people interlink them with belts, but it's actually easier just to add another motor. Then you've got your X-axis, Y-axis, and then another motor to actually extrude the plastic. So 5 motors times $15 each, $75. You're gonna have some sort of driver board. This is what actually takes your code and converts it to the signals required for the motors. It's gonna be around $150. Power supply of some kind. You can use a old PC power supply, which you probably have laying around. But if you don't have one of those, $50. So it all adds up. So just this is like $375. A lot of people ask, what's the cheapest I can make a 3D printer? Well, here are the bare minimum parts you need, and you're going to be spending $300 or $400 just doing that. And that's not even before you get to the hardware, the frame, the belts, the pulleys. It can add up pretty quick. And at that point, if you're thinking that, hey, I'm going to build my own printer, no matter what, you're going to spend like $400 or $500. So you're usually better off getting a kit, because at least that's known to work. As long as you follow the instructions, you'll get a working 3D printer out of it. Instead of like, hey, I'm gonna try to build one for $350, oh, and it doesn't work, and now I don't have a printer, or $350. Kits. All right, let's talk about filament. There's two major types of filament that people use, ABS and PLA. I keep a lot of ABS in stock because it's the type I prefer, but I also have some PLA, so I can talk about the differences. Let's grab some of this. So this is ABS, this is PLA. So major differences between them. ABS is usually stronger. It's pretty much exactly what they use in any sort of consumer product, like your video game controller or what's housing your computer monitor. PLA is kind of a newer thing. It's actually made from corn usually. It's organic. So, it's good for the environment. However, being organic, it can biodegrade, and it's also not as strong as ABS. A good thing about it though, is when you're printing something larger on your heated bed, it's much less likely to contract upon itself, causing the edges to lift up. Whereas ABS, unless you're careful, likes to do that. Of course, you can counteract that by putting some hairspray on your surface, keeping the bottom layer of ABS stuck down. PLA is crunchier. It tends to chip. See that? And it also breaks. It's kind of like spaghetti. Whereas ABS will bend. See that? And if you try to carve it with your knife, it'll carve off in long pieces rather than chip. So if you have some material you're not sure what it is, bending it or using your knife is a good way to test. Same thing with acrylic versus polycarbonate. So PLA is popular, but for me, I like ABS. I'm going to keep using it until I can no longer get it. Now let's talk about the process for obtaining or designing files for 3D printing. 3D printers require special files in order to print them. Typically they use something called an STL file, which stands for Surface Tessellation Language, not to be confused with an STL printer, which means stereolithography. There are several ways to get an STL file. If you wanted to print something existing, a great place to go is Thingiverse, which is actually owned by MakerBot. Let's say we want to, print out a TARDIS. Well, look, they have one right here. Someone's already designed it. And usually they have the source files too, so you can modify it and make your own version if they say you are allowed to. So if you need like a chip clip or you just want to test your 3D printer, Thingiverse or other similar sites are a great resource for that. Another way to make your 3D print is to design something yourself. You can use Blender or Autodesk 123D or Sculpt. There's many free programs that you can use to make something. So, I can make a box here, and you've probably seen me do this before on the show. Oh, that's not very impressive looking. There, so. You can use a free program to create your own STL files, and then in this case, I would just export STL. Another way to do it, which is kind of hardcore, is to use OpenSCAD, which is a programmer's 3D modeling language. You don't actually draw it with pixels and splines, you actually program what you want to see. Let me show an example here. Let's grab this one. So this here is the code that tells the modeler what to draw. And in this preview window, we can see the result. In this example, I've downloaded an OpenSCAD file to make a pulley, and here are all the parameters. So I can actually change these and then re-render and see how it changes over here. So yeah, this is a very good way to make precise parts, for your 3D printer or anything else you might need. You could have a gear generator for this, pulley generator, rack and pinion, really pretty much anything. So it's kind of a hardcore way of making parts, but it's also a very good way. And then when you're done, just like anything else, I can export as STL.
Now it's time for a tech timeout.
For today's Tech Timeout, we're going to answer a question we've been seeing in the comments. Why don't I use my solder gauntlet for everyday soldering on the show? Well, the reason I don't is because the gauntlet was meant for location soldering, like, oh, I'm in my car or I'm inside of a machine. If you're at your desk, nothing beats a standalone iron, so that's why I wouldn't be using these at my desk, because this is better. Once you have your STL file ready, you need to slice it. Now, slicing is a process of taking the 3D file and turning it into multiple layers that are printed one at a time, like slices. How you slice it is going to depend on what kind of printer and what kind of driver you have. I will take you through the slicing programs that I have installed on this computer. This one is the MakerWare slicing program. This is the one that you use with the MakerBot replicator or one of the older cupcakes. And you basically import the object you want, and then this here represents the size of the bed. So if you want to print multiple objects, you can actually just copy and paste them, see that? And put them wherever you want, and that's where they will print. It's pretty easy to see where they're going to work. And since I have a dual head extruder, I can actually say that, let's say I want some of these to be printed with the left extruder. And by setting the color, the machine knows what to do. Let me show you the next program. This is Replicator G. This is an older program. This was kind of the de facto standard for a while. And this is what actually originally came with the MakerBot. It does the same thing. You put your object into 3D space, although the 3D space navigation isn't as smooth. And then you generate G-code using whichever slicer you've selected. And the nice thing about this is you can plug in whatever slicer you want. It has a built-in one, or you can get like slicer, which is a type of slicer, but the E is a 3. And yeah, and a lot of the settings are going to be the same. The main thing that you set when you're slicing files are the thickness of each layer. Typically it's going to be the diameter of the nozzle or less. So if you have a 0.35 diameter nozzle, the coarsest print you might want to make is 0.3 millimeters. 0.1 millimeters would be a fine print. And infill and other things. This is the Cube software for the 3D Systems Cube printer. That's the fairly cube-shaped printer that you can actually go and buy at like Staples or Home Depot. And I have one of those as well. Now this software is fairly simplified. You basically just bring it in and you can set a few things like, inches or millimeters, not that that really matters, raft on or off, support, and hollow, strong, solid. So it's kind of dumbed down. It does work though. And of course, what type of plastic you're using. The reason the type of plastic you're using is important is because the temperature setting is different for PLA or ABS. PLA can actually be done at a lower temperature. All right, I'm gonna go back over here to the MakerBot. Let's get rid of some of these. Let's just do one here. Let's say, okay, that's what I want to print. So I'm gonna go to Make. All right, so here are our options. Now, you can just do low, standard, higher, but I like more options than that. So let's go down here. So temperature and speed, we don't really need to mess with, but infill, this is what's important. On your printed pieces, see that honeycomb pattern? It doesn't print this completely solid plastic that would take a lot of plastic and also a lot of time. It will print like a lattice inside of it, which will give it support, but without using up all the material. So that's called your infill percentage. This is probably about 10%. The higher the infill percentage, the more material will be inside of it. Anything over 25 is usually overkill. Shells are how many layers it puts along the edge. So this has 2 shells, which means there's going to be 2 layers of walls for any edge and also 2 layers at the top and the bottom. And layer height is the thickness of the layers. 0.2 is pretty good. You probably can't even see the layers on camera, but they are there. Earlier I mentioned that sometimes ABS prints can lift up on the edges. One way you can avoid that is by having a raft. Let me show you an example. A raft is where it kind of prints a structure below the object, kind of so it has like, well, like a raft to sit on. The reason for that is it gives it more surface area, so it sticks to the bed better. And if you're not using a heated bed, rafts can be even more important. So I'm actually gonna print a raft here so you can see what it looks like. Now supports, that's another thing. Normally if you print something, it just goes straight up, but if you have an overhang, if you can't print plastic in midair, what supports does is it kind of builds like a little, almost like a little scaffolding automatically under bridges and whatnot to kind of support them. I'll make an example of that too. To finish this up, we're going to take a look at several 3D printed parts. So here's 2 different examples of the same part. One has a square inner edge and one has a rounded edge. The reason I did this was because one is stronger than the other. Oh no, it broke. Happy Thanksgiving. Okay, so if you've got the room, always put rounded corners inside of objects because as you could see, I had a much harder time breaking that. I mean, this one was like super easy in comparison. Also, you can't really print overhangs. If we take a look at this one, this was printed with no supports and see the sagging here? I mean, it did work, but the first few layers sagged and then these are solid because they're above the first few layers. But what you can do is say that you want to print with supports. And see this right here? It auto-generated a support material to keep this straight. So when it did print the top, it had something supporting it. And the support material is meant to easily break away. See that? Now you have the same shape, but it's got a nice flat bottom as you intended. If you do need to reinforce it, I suggest using some super glue. You can use super glue or acetone. Acetone will dissolve ABS, but it also will seal it. So what's going to break on your 3D prints are the layers. That's where the least amount of bond is. So you want to reinforce those layers with a little bit of glue, especially where you think it might take some damage. All right, while that dries, I'm going to show you something else. This was the piece we printed with the raft. So the raft is a single layer that helps keep the piece flat. And if you don't have a heated platform, rafts are even more useful. And like the support, it's meant to more or less easily pull away. Now this piece is also an example of a screw mount. You can make a piece that just has a hole in it like this one does. And I didn't make anything special, I just made a solid block with a hole going through it for the screw. And in this case, it's meant to take a size 6 screw, which means you have a hole that is 1/8 of an inch, and the threads are a little bit thicker than that. Threads are usually like 0.135. So what can happen is as you drive the screw, you can cause the inner cylinder to break free from the top and the bottom and then free spin. And at that point, the screw won't go any further, and it's also really hard to retract. Basically ruins it. What I'd suggest is whenever you can, model your screw base individually. So the idea here is we put the screw in through the top, but in the piece we have an extra thick wall around the screw, and then we also have a curved connection here, which is called a fillet, that gives it additional surface area and makes it stronger. To hedge your bets when making screws, you should use a tap like this. What this does is this puts the proper threads in the material to match the screw you want to use. In this case, I'm using a size 6 screw tap, which would be a 6/32, 32 meaning there's 32 threads per inch. Now yes, cramming a screw into material will also create threads, but this is the proper way to do it. And if you're using a 3D printed piece, which is inherently weaker than other materials, this is a good idea to do. It takes longer, but how long does it take to reprint your ruined print? Yeah, think about that. Now when I put the screw in, oh yeah, look how easily it goes because the threads are already there. And this tap is meant to make holes, so it's much less likely to cause cracking than just cramming the screw in itself will. Something else you might notice on these is the bottom surface tends to flare out a little bit. It's because that's the first layer that gets printed, and sometimes it gets a little squished onto the bed. Now proper bed alignment can fix this, making sure the bed's are the right Z-axis. But, they get out of whack pretty easily, so I usually just fix these with a little bit of sandpaper, if it's even necessary. Just a little bit to level them off. They're good to go. Yeah. Let's go back to this super glue one. All right. See if this one's harder or easier to break. Well, okay. It wasn't still as tough as the curved one, but it held up better than this guy, which, is easy to break. Obviously, if you have thicker walls, it's going to be stronger, but still, when they break, it's always right on the layer. See that? You can also see the honeycomb pattern inside. Yeah. All right, well, there are some tips that will help you not only get your 3D prints done correctly, but make them work well after they've been printed, because it's not just about the machines. Prep time and cleanup time is a big part of it. That's all the time we have for today. In our next episode, we're going to build a Raspberry Pi-based point-and-shoot camera. We'll see you then.
saw.
3, 2, 1. Mark. Your Titan is ready for launch. Jacob Smith says, wow, you couldn't even make it look like MC. I assume that means Minecraft blocks. Lazy. Yes, I'm sorry that me spending 60 hours on interlocking Minecraft blocks was so lazy.
The Ben Heck Show is brought to you by Element 14, the electronic design community and online store built for engineers and hobbyists alike. Join now and browse the store at element14.com.